we're going to take a look at setting up an integral representing the surface area for a surface which happens to be the graph of a function called g with two inputs x and y. So the surface we'll look at is the surface defined by this. It's the graph of the function g of xy is equal to x cubed times y to the seventh, and we'll only look at this particular, well, this actually happens to be a square. I don't think I necessarily meant that, but it's a square of side length 7 on each side. So imagine in the xy plane you've got a square from x going from 1 to 8 and y going from 2 to 9, and above each of those points in that square of area 49 square units, you have a z-coordinate given by this graph. And so all of those points that are above, we're going to treat those all as the points in the surface S, and we're going to set up an integral representing the surface area. You could basically parameterize this thing by just saying x is equal to u, y is equal to v, and then, well, z should be pretty obvious just by plugging in x is u and y is v. But instead of doing that, we're just going to say r of x, y is equal to x comma y comma x cubed y to the seventh. And if you run through all the same thing you normally would for a parameterized surface, well, here's our parameter domain. And if you run through what is the norm of the cross product of r sub u times r sub v, you would actually end up getting this expression, just speaking generally, and for this particular example, that's square root of 1 plus here's the partial with respect to x, then there's a square from the formula, plus here's the partial with respect to y, and then the square. And so when you set up the area, the parameter domain was x going from 1 through 8, y going from 2 to 9, and we needed this. This is the thing that represents the norm of the cross product of ru and rv, and then the dA turns into dx dy.